Thank you, Jens. So this is really work. It's part of the PhD work of my student Benno Stein, and he couldn't be here, so I get the opportunity to talk to you today. Okay, so all right, so here's the context. Today, when a developer submits a code review, then often it's commented by their team members, but now also increasingly it's commented by a bot, right? That is backed by a static analyzer. And what we want to do is make the static analyzers do a bunch of thorough reasoning to flag semantically deep issues to help us build better software, right? So let's suppose we're in this great situation where this analyzer flags some deep and real and important issue. Then, well, now the developer, when they wakes up, they want to kind of fix that, right? And submit a bunch of changes. And if they do this now today, then it's going to take a while. Right, and this is going to be a kind of frustrating experience because, well, really, maybe it's just a one-line change that they have to do, or they just care about the error that was flagged at line 8. Right? So the need here is to make analysis interactive, right? To make it incremental on these edits, on these subsequent edits, and demand-driven on queries, this particular query on line 8. Right? So this is the task that we set out to do, that the analyze user needs this to be interactive as they make edits and issue queries, but also that we want it to be consistent with the underlying batch analyzer that ran overnight. And then now also what we're thinking is that the analysis designer doesn't really want to implement 2 versions, right? This really needs to be push button, and they don't need to sort of ad hoc think about criminalization. And it needs to be general with respect to whatever abstract domains they already implemented for their batch analyzer. So let me unpack what a static analyzer looks like today often. So behind that magic that takes a program and produces an over-approximate set of facts, there's usually 2 parts. One part is what's called the abstract domain, which assigns the set of abstract states or facts that you care about the program, and then operations over it, like transfer functions, join, wide, and so forth, right? And then a separate part that is like a very generic abstract interpretation engine. So for example, using the standard work list-based fixed point algorithm. Now this picture that I'm drawing here is intentionally very, very classical. And why? Because it's very general and a well-studied soundness theory. Right? So in fact, the focus here is on general. We want to support whatever infinite height abstract domains you care about. It doesn't need to have a best abstraction. However, you need to do to reason about your program. Right? So now if we look at an interactive abstract interpretation framework that we're trying to build, what we're trying to do is really just drop that standard engine and replace it one that is a demanded abstract interpretation engine that supports demand-driven queries. What is the abstract state at this program location? Incremental reevaluation on edits to add, edit, or delete statements, and then have strong consistency results, what we call from-scratch consistency, right? That query responses are guaranteed to be the same as the batch analysis on the current program version. Right? And in particular, this domain interface should remain unchanged. In my animation, nothing changed, right? Okay. All right. Okay. So. Right, so we did this a little bit, right, in some prior work on reifying an abstract interpretation computation, right? Essentially taking that computation and putting it into a structure that we call a demanded abstract interpretation graph, or a DAG, that reifies the dependency structure of that abstract interpretation computation. Right? And what that's composed of is reference cell vertices that cache program syntax and abstract states in order to be incremental, and that could be potentially empty to support demand. Right? And then these vertices were connected by computation edges that acyclically connect those and are labeled by these domain functions like the transfer functions, join and widen. Right? So let me draw a little picture of that. Right? So here, the gear here kind of represents the abstract interpreter crawling over a control flow graph here with just a single statement S. Right? And that reification, sort of the corresponding DAG snippet, looks something like this, right? We have boxes to represent cells here that cache states. And then between those cells are analysis computation labels, right? And so this is that reification of the abstract interpretation I'm talking about, waiting to be demanded, right? So that is, if we care about, like, oh, we want to ask what is the abstract state at L prime, we want to demand there. Then demand might need to go recursively backwards to compute the state at L. But once it has that, then it just applies the analysis computation label and gets us 5' here. Okay. Right? Now, if we have some edit here, that statement changes from S to S prime, then we just dirty and mark everything forward, right, for later incremental reevaluation if it's demanded again. Okay. Very simple picture, right? this all makes sense if it's acyclic, like in this picture, right? But cyclic dependencies will make query evaluation undefined, and so that's kind of the tricky part here. Okay, so if we pop back up to where we are today, right, this picture, right, this is what we want to support, right? Then that all works from this prior work if, we just have a single control flow graph, if we just have main, right? But of course, real programs have procedures, right? Main calls foo calls bar, right? And so then what is that sort of corresponding engine here, right? And that's what we're going to talk about today. That supports demand-driven queries, incremental reevaluations, now with procedures, but also importantly, we want to guarantee from scratch consistent results. Okay? All right, and of course, the hard part here is like, well, what if bar is recursive and programs, that have recursion, have loops, so how do we do that? And that's what we call demand and summarization. All right, so the contributions of this particular paper are about really this demand and summarization. So we introduced the idea of a demand and summarization graph that reifies the dependency structure of a summary-based abstract interpretation computation. A DSG turns cyclic dependencies, or sort of what would naturally be cyclic dependencies from recursion, into acyclic DAGs with self-referential demanded summaries, and I'll say what that is. And then we have a formalization where we are, careful formalization to prove that demanded summarization is terminating and from scratch consistent, okay, and therefore sound. Right? If it's consistent with the batch analyzer sound, then from scratch consistent demanded analyzer would be sound. Okay, so let me sketch the kind of idea here of a demanded summarization graph. Or I guess first I'm going to kind of put out the naive approach, right? Is that we could build one big interprocedural DAG, right? Combine all the control flow graphs into one, conceptually into interprocedural flow graph, and then build a single interprocedural DAG structure, right? So take the CFGs from those procedures, their corresponding DAGs, wire them together with call return edges, right? Now, of course, we just directly do that with recursion. We're going to break that acyclicity invariant. Okay. And also, it just doesn't feel quite right because it really doesn't leverage procedural abstraction because in this structure, if we edit like at the beginning of the program, then everything through the entire program becomes dirty. Right? So we don't have, right. So it kind of feels overly conservative. Okay, so in our approach of a demanded summarization graph, okay, so a DSG reifies the dependency structure of a summary-based abstract interpretation computation. Okay, so what are those pieces? Now our vertices are going to be DAGs themselves that compute procedure summaries on demand. Right? So if I have main, foo, and bar, then now the corresponding DAGs can correspond to procedure summaries. Right? Or really, the DSG doesn't really care what's underneath. You could have some other way to compute procedure summaries, but for concreteness, I'm going to instantiate them with DAGs. Now, then what a DSG sort of represents is summarization edges that connect the return cells, the DAGs that need to use procedure summaries with the procedure summaries that we demand. Right? So then the overall structure is a DSG of demanded DAGs. Now, if we have recursion in our, in bar, in our program, right, then we record, some sort of self-referential summary applications as interprocedural dependencies, but because of this hierarchy of DSG and DAGs underneath, then we kind of maintain the acyclicity invariant. Okay, so let me illustrate that. Okay, so DSGs record the use of a procedure summary. So here, this is our running example where main calls foo. So if we were trying to get the state at L prime, the DAG evaluation gets stuck at L prime, depends on a summary of foo. Okay. So at that point, we might construct or maybe reuse something that already exists, a DAG for the callee, initializing that entry location at L. And then we'll just demand the, and query at the exit to get phi prime at the exit. And then this fully solved DAG is effectively a Hoare-style procedure summary, very classical, and we're used to, that we can just apply back and say, well, the state at L prime is phi prime. But importantly, when we do that application, we record that dependency. Right? So this DSG edge that we introduce in purple here is that L prime in main depends on the summary of foo with its procedure entry state phi. Right? And then we would dirty L prime if this particular summary is ever dirtied. Now we do leverage procedural abstraction. It's compositional, and that edits in the callers will never affect any of these further demanded summaries. Right? There is no sort of edge from at the call site, for example. Okay, so let me say a little bit about the complexities of recursion. So with self-referential demanded summaries, right? So yes, there's going to, recursion means there's going to be a fixed point iteration. That should not be a surprise, right? But the hierarchy between the DSG and DAGs prevents, this sort of dreaded cyclic dependencies. Okay, so in our example, bar is recursive. Bar calls itself. So embedded in the bar DAG, there's a call to itself. Right? So maybe we can demand up to the call site and get phi call. Now, if we're trying to get L prime, we'll discover that we want to reuse this same summary that we're in the middle of computing, right? Because phi call is included in phi. And this is what we call a self-referential summary query. Now, doing kind of essentially the same thing as before, right, is that we want to query at its exit state, but we want to specifically say query for its exit state at fixed point. And that might need to use this interprocedural DAG dirtying, to do this iteration. But, after that's done, then really it's kind of the same, right? There's now a dependency at the return site to itself, it happens to be, but it really is the same picture, right? A DSG edge, L prime and bar depends on the self-referential summary of bar with a procedure entry state phi. Okay? But importantly, each of the underlying DAGs remains acyclic, and so the dirtying and querying algorithm kind of remain okay. All right, let's see time. All right, okay, so that's the taste, right? So let me give a taste of the formalization, right? So interactive summary-based abstract interpretation is realized through two parts, right? One part is this demand-driven query evaluation that creates a summary use dependencies that says, in a DSG, a query at L under entry state phi, yields a state L phi prime at L, and an updated DSG. Right, and we kind of talked that there's, that depends on 2 bits that might generate summary edges, right? That if we're stuck at n, then we need to get a procedure summary that adds a summary dependency edge. Or if we're in some recursive situation and we demand a self-referential summary, then we have some recursive summary dependency. But once we have that, then, we're in a situation where in DSG that we have a subsequent edit, right? That, an edit of cell n, with statement S, just results in yields a dirty DSG, and we can sort of continue this process. Right? But the summary here is that, demanded summary use dependencies that we create through this query evaluation that we carefully created enables this proof of from scratch consistency. All right. Okay, so does this work? Let me show you a little bit about that, right? So in fact, our goal of being interactive, does demanded summarization enable responsive queries after edits? Okay. So what we did was generate random program edits with looped procedures, conditionals, using a probabilistic grammar, right? And comparing an analysis, in this case, trying to use a precise or a deep analysis using octagons, right? And compare the latency for 4 configurations, 3 baselines or batch, incremental, demand-driven, and then demanded, which is the combination of the 2, incremental, demand-driven, on a sequence of 2,500 edits. Okay? So that's the setup. Let me show you kind of one way of looking at this data. So here's a cumulative distribution graph where the y-axis is the fraction that are completed within the sort of analysis latency on the x-axis. Okay? So that is, if I draw this sort of 95th percentile line, or P95, then wherever it crosses the point is the 95th percentile will complete within that n-second latency. Okay. So taking that data, I can sort of summarize it into a table on the right, where of these, again, these 4 configurations, right? So the mean and P50 show that there's already some separation demanded. It starts to separate it more at the P95 level, and that P99 at the 99th percentile slowest run, right? Then the separation really becomes quite evident. So this provides some evidence for mitigating the sort of worst case analysis cost, right? We don't, we want to, really in the tail that we want to sort of enable for interactivity. All right, so how about in practice? How much does demanded summarization reduce reanalysis in practice? Okay, so for this, there's this very nice data set out there on the bug swarm data set. Of real Java bug fix pairs mined from GitHub. So that means we can get a particular commit with an edit. So here are those benchmarks and the lines of code of those benchmarks. And then the second column are the number of lines that are edited in that particular commit. Okay. So then we consider running analysis with 3 different abstract domains: intervals, octagons, and nulls. I'm only showing the summaries for the octagons and nulls because of space, but they're there, right, in the paper. And then now on the initial version, we run the batch analysis. So that's, imagine the overnight run, right? That's the number of states that get computed by that sort of batch analysis. And then in the 3 subsequent configurations I'm showing the percentage of the batch states that need to be recomputed on the edit, right? In the sort of incremental but not demand-driven, the demand-driven but not incremental, and the demanded version. And really, I guess the take-home message is that we're really only recomputing a very small number of the overall number of states that the batch analysis does, either from 0.1 to 2.7%. Right? Okay. All right, so timing right on. So in conclusion, a demanded summarization graph reifies the dependency structure of a summary-based abstract interpretation computation. A DSG turns cyclic dependencies from recursion into acyclic DEGs with sufferential demanded summaries. And we've done a careful formalization where we've proven demanded summarization terminating and from scratch consistent and therefore sound. So with that, I show you a beautiful picture of Boulder for you to come visit. And then otherwise, I'm happy to take your questions.
Thank you. We have a microphone. Come up, come up.
Thanks for the great talk. I'm curious how widening fits into this framework.
Yeah, so the widening becomes part of the engine. And so whatever widening is supported in terms of your infinite height domains. And just like I showed in the recursion, the widening gets used in that sort of fixed point computation, the sort of usual thing, unless you had a more specific question I'm missing.
I guess there's the issue of one could the widening heuristics, like when to apply widening, might not be stable because those exist outside of the fixed point definition.
Yeah, so I mean, it does say that our engine kind of fixes a particular widening strategy, or you sort of count on the widening strategies that our engine would provide, right? And of course, that would be a great thing to think about how to make that under the control of the analysis designer versus the framework. But so yeah, exactly. That becomes great, excellent future work.
Thank you for an interesting talk. My question is regarding the recursion. Does your approach handle indirect recursion via multiple functions? Or is there anything that has to be added or extended in that situation, if there is a cycle in the call graph involving more than one method?
Yes, okay. So the tricky part, of course, is detecting when you need to switch gears from the normal sort of summary dependency introduction and when you need to introduce a self-referential summary. So if you wanted to sort of, if you will, pre-compute the sort of like a strongly connected component and say, oh, whenever you're in that, then it's a self-referential summary, then you could do that. For the simplicity of our formalization, we just do it where we assume you only have sort of single recursion. Or you can think about it as like, oh, you translated all mutual recursion into like, one method that dispatches between them recursively, something like that, right?
Thank you.
Yeah, good question.
Following up on that question, imagine a kind of a worst-case program. You have an entry point that calls a method, that calls all of the other stuff in the program, then returns to the first method. In that case, wouldn't kind of much of the performance be lost because you would then have a self-recursive call that kind of includes your entire program? I mean, wouldn't it then make sense to have a mechanism to say, hey, I know that the stuff in the middle is kind of totally unchanged, and we can somehow pull it out of that loop?
So you're saying if you have an edit at the top and you sort of like, would that sort of dirty everything or something?
Yes, yes.
So exactly, that's kind of the nice bit of our approach is that it doesn't. Because there's no dirtying of the subsequent summaries if it's just an edit that's sort of the beginning of the program because there's no sort of call dependency.
Okay, I was just wondering because then, following up to the previous question, you don't have this self-recursive or self-referencing summary from one function to itself, but to kind of a much higher point on the call stack.
So the question, well, it just depends on how, like, the summaries that make sense in the intermediary would be fine and unchanged, right?
Right, and can you detect this then?
I mean, I guess I can't say that we've empirically tried it, but it
Okay.
seems like this would be possible. So, I mean, it's kind of in the details that we would have to sort of think about.
Thank you.
Yeah.
Very good. Let's thank the speaker again.
Yeah, thank you.